So, thank you very much for submitting to the workshop and for presenting. I would like to welcome Iva to the stage from SAP, and she's going to talk to us about resource optimization in distributed systems for SAP HANA. Thank you so much. The stage is yours.
Thank you very much. So, hello to everyone. My name is Iva, and today I'm here to represent engineering teams from SAP Korea and SAP SE. Together in the room is also Hanyoung, but I'll be presenting. And as you can see from the slides title, our topic today is resource optimization in distributed systems. And more specifically, I'm going to talk about SAP HANA CI resource optimization. To begin shortly with and to give you a little bit of background, usually when we are talking about resource management, DevOps teams and infrastructure, they're talking about micro-level code performance rules, right? So here, what really puts strengths on our hardware is not actually the code, but the resource allocation and how we manage this. So in today's presentation, 20-30 minutes maybe, I know you're hungry. I'm going to introduce you how we manage our resource allocation in SAP HANA CI. But before that, let me walk you through the agenda. So first you have the challenges. Challenges maybe that every big enterprise, large-scale CI/CD system have experience with resource management. Then we will go through a little overview of SAP HANA CI system and how we run it through a graph-based framework. And then starting with the solution of our problem, I'll introduce to you the intelligent orchestration service that we have implemented. I'll introduce to you an example and also high-level architecture overview of the system. And to have a little bit more of a deep dive, I'll introduce to you the machine learning models we have used for our first project in resource optimization. And then to give you the full picture, to make a full round, I'll introduce to you some modeling results and some real-world impact in production and our future work. So to begin with the challenges in large-scale CI/CD systems, as you can see, very flow that you're all used to see. Developer commits, and this commit and push to the repository, of course, triggers CI event. CI on its head has to schedule all the tests, and he has to allocate resources for those tests. But here I put also sample data from SAP. We have around 800 commits per day. This results in about 2,000 builds. 2,000 builds, and then this is around 1 million tests per day, right? And this is all executed on 1,000 heterogeneous nodes. So while CI has to allocate resources, CI does not really know those resources. How much do we need for the particular build, for the particular test? These resources, they're all defined based on expert heuristics. And what are those expert heuristics? They're static buckets of resource requirements based on historical data, based on the developer's know-how. And developers, they usually don't want to have failures in their builds based on out-of-memory events, is the example here, right? When you have an out-of-memory event, this eventually leads to your build to fail. You have to restart everything. And maybe if you're into, let's say, 2 hours into a build, into a testing, and you have to restart everything, then you can imagine that you have to do everything from the start again. You waste 2 more hours, you waste additional time also to finish your run. So developers, they just use safety first, right? So we need additional memory just in case to prepare for the worst case scenario. And this on the infrastructure side, it costs us money, it costs us resources, and also reduces our velocity. This meaning that while those resources that are put just for the safety buffer, they just stay idle. We might not need them really. And instead of using them for executing on other tasks, they're just staying idle. And our queue of tasks is just growing and growing, but then we cannot utilize it. Let's see how this translates into SAP HANA CI framework. So here I have ignored the developer that pushes the code, but when a developer pushes the code, you can see each commit, each change of the code that's translated into a commit. I push to the repository and then the CI triggers, and the CI has to execute the verification run, for example. So this run has to execute a lot of tasks. There has to compile, containerize, and also do data-heavy validations. It's not a straightforward. It's not linear. We shatter every commit to a lot of little tasks. We connect them, so you can see it's a graph-based framework. So every task is a node, and sometimes they can have dependencies between themselves. And those dependencies, in the case of SAP HANA, it can be mock tables for the database. It can be input or output values. They can be very different. So we cannot just zip everything into a file and just pass it between the tasks, right? That's why we are using also integrated storage management layer. With that layer, the tasks before execution, they can pull, or after execution, they also can write it. Each task has a requirements. These are the requirements I told you that developers define. Each task has, for example, a location requirement where it has to be executed, or maybe how many CPU does it need, or how memory does it need. And so after CI is triggered, it reads all this data and then proceeds to schedule a task for execution. And then when task is being scheduled for execution, it has to be placed also on the right node, right? So in SAP HANA CI framework, we have around 1,000 heterogeneous nodes. They can be a simple virtual machines, like 64 gigabyte virtual machine on the cloud, or maybe big power PC machines for more big tests. There are scale testing that we have to do. So the scheduler gets the task, reads the requirements, and places the task on the right node for execution. In this example here, the scheduler is placing each task on each node, but you can see that sometimes we can have memory that's left that can be used from another task, or there might not be exactly enough memory. So tasks have to be placed in different nodes, and so this is the ways that we're actually talking about. And now, about the solution, what we did, we got more than 300,000 runs that were executed over 8 weeks. We got 300,000 runs, and we analyzed how much memory they are using per build and how much memory is actually left. So the numbers were not that good, as you can imagine. For example, I think it was around 60% memory that was not actually used in runs, which is a very big waste, and we can use that idle memory to schedule and do other things, right? So for our first project in resource optimization, we did it over HANA build tasks, and we optimized the memory that is being used for those tasks. But here, in large enterprise CI like SAP HANA's, we cannot just rewrite the whole CI framework, right? We have to put that optimization in such a way that we can just, let's say, plug it in and start using it, and if we don't need it, maybe pull it out. So what we decided to do is implement additional service that will be connected to the scheduler. It will get the tasks requirements. It will intercept the task before it's scheduled, get its requirements, optimize the memory, and then return the data to the scheduler. Meanwhile, the task is on queue, waiting to be placed as node. And while when the task gets its new requirements, as you can see, this was before task 2 is scheduled as it used to be, but currently, for example, we have optimized HANA build task number 1. It gets less memory, so now we also can use the first node to schedule again task 2, and then we have one free node with more memory that we can use for other tasks. Now let's see more about the technical implementation of this orchestration service. We did it as a microservice based on Fast API framework that intercepts the data from the scheduler, and data is being registered in the service, and then through background tasks we are putting it from the database, and then on its hand sent for refinement. Here we have 2 more services that are a core service and then a memory refinement service. On memory refinement service is sending all the data to the machine learning memory predictor here. Memory predictor does its magic and then returns the data back, and we send the data back again to the scheduler with new requirements. Why we did so many services, you might say that there are too many components here, but what we essentially wanted to do is make a highly modular application where you can put services, add, remove them, enable or disable them. Or also we wanted to have flexibility, because for one task we might also want to refine not only memory, but we might also want to refine CPU, for example, or location. So having one core service that orchestrates the things, dispatches everything where it needs, and also making the data having a template data, because when we return the data, we can actually turn it in all kind of formats, right? The core service organizes everything and dispatches everything, while the additional services, we just use them as in a plug and play kind of way. So we have greater flexibility, and we can, as I said, plug and play everything. And now let's look more under what's under the hood. Here we have what we have used for the machine learning predictor. We have chose ensemble combination of the machine learning models like TPM and XGBoost. So we use them to predict memory requirements based on high-dimensional field measurement. As I mentioned earlier, we used more than 300,000 historical fields in 8 weeks, in a span of 8 weeks. And we to use only let's say average metrics for prediction of the memory is not enough. because in large enterprises systems, the memory that the task uses are not are asymmetrical. They are not always the same. We might have a big code change or just simple documentation change. So the task does not always use every time the same memory. That's why here one also important thing is that while predicting the memory, we cannot have out of memory failures. As explained earlier, out of memory failure just means killing productivity and having you to restart everything, to wait more, and this is a situation that we do not want to have. So by utilizing quantile regression targeting the 59th percentile, here we heavily penalized the under allocation, and we got the safety first bias for the model, meaning that even though we can have a little bit of over allocation of memory, this means that we are using a little bit more resources in just a short time or maybe temporary time, which is fine. But then we don't have failures in our builds. And data also is paid, the model, I'm sorry, the model is also based on a feature engineering. We used rolling window statistics of five last historical builds. We used build profiles, branch signals, and compiler metadata. Here, the rolling window of 5 historical builds gave us also the ability to know if this is just a code change or maybe a documentation change, and be able to predict how much memory we are going to need. And last but not least, also we have predictions that are bounded by 1.2 safety multiplier, just for safety. And then to show you some of the modeling results here, as you can see, the gray is the baseline data set. Most of our builds were in over allocating zone. This was more than 60% of the builds were in the over allocating zone. Over allocating means more stale memory, more idle memory that we are not using, that can be utilized in other works, right? And after applying the sample of those two machine learning models, we got just the difference of well allocating. You can see the green bar is right now the builds are in around 80%, let's say around 80% in well allocated zone. And this compared to the gray is 48% difference, which is quite a big difference. And now the waste categories called here: massively over allocating, extremely over allocating, it's very over allocating. We have 68% of reduction for them, which is really big number. And for the next slide, you can see that how this number translates in our monthly results. But first, the risk mitigation. So we were talking about out-of-memory events. Here, if a build goes into under allocation, it means that we're getting out-of-memory events, and now we get a smarter prediction that results in 99.7% out-of-memory free prediction. This is, of course, again, let me mention the multiplier for the safety. As mentioned, we might waste some resources, but then we don't have failures, which are essentially increasing our productivity too, and we are utilizing memory a lot better. because what we wanted to do, if we only reduce memory, but our builds start to fail and we have to restart everything, we got errors, we also essentially are failing in our task. But here you can see that there are some trade-offs, but still we managed to find a good balance between well-allocated memory and a bit of wasting our resources. And now, before concluding the monthly operational impact, what we have here is that for each build, on average, we save around 36 gigabytes of memory. This is also, let's say, the safety buffer that we managed to recover from the runs. At the beginning of this session, I mentioned to you that developers, when they define what kind of requirements does a task need based on the historical data and also on their precautions of failures. And I mentioned to you that also 60%, more than 60% of the data, the memory that we are actually more than 60%, around 60% of the memory is not getting utilized properly. So this number now translates to 36 gigabytes per build. And also aggregated in total cluster memory footprint, we get optimization ratio around 20%. And maybe the most important metric here is also how much capacity we have spent. This can translate to 2.8 petabytes per hour, and this is operational capacity time reclaimed for builds without queuing. And based on those results, what we can conclude as our future work, currently we are optimizing memory only for build tasks in SAP HANA CI, but what we can do is apply those models and extend the memory prediction to our tests, because we have unit integration, large GUI, and performance tests for every build. Those tests, they're significantly many numbers than the builds. If you can remember on one of the first slides, I mentioned to you that we have made around 1 billion tests per day. So optimizing more memory means that that we save more per unit of time, and also we can expand those optimizations not only to the memory of the tests, but to a multidimensional modeling and utilizing the orchestration service to optimize not only memory but CPU resource requirements of our tasks. And with that, my presentation concludes. I'm now happy to take your questions. Thank you very much for listening.
Thank you so much, Iva. So given that we started a little late, I would say we have 5 more questions before we go to lunch. Any questions for Iva? Yes, please.
Hi, great talk. Yeah, I was curious, did you say that you used an ensemble of 2 different tree models, right?
Two models, yes.
Okay. And yeah, I'm kind of curious what performance difference you saw with that choice versus like compared to other models that you tried.
Related to the performance, I don't remember exactly numbers.
Oh, no worries.
Yeah. I don't remember exactly numbers, but here those models were chosen because of their fast metrics operations over the metadata.
Okay, and so you're training them independently and then averaging between the two, or?
I'm sorry, I cannot answer that. Maybe behind that.
The answer to your question, we did classification first. So classification, like we did for like XGBoost classification, like distribution and like forest and so on. But compared to that, and some of it is the regression model. So those models outperform the classification. So we used the hotel regression ensemble model, and that model was the next question. Well, we did the hyperparameter optimization for two models parameter in how they say the same loop. So yeah, yeah.
Yeah, so you were saying like you were going to do a future study on multidimensional like concurrent interpolation of memory limits. I was just wondering how you plan on doing that, and also if you're planning on doing like checks for how long each of these tests will run when they're run together, and some sort of analysis on that, and if you have any ideas for how you will accomplish this.
Currently, it's only included in our future work. So I cannot answer you exactly how we are planning to do that, right? But as it was explained here in the architecture, so we are doing this so we can do not only memory, but together with the CPU and memory. So of course, this all will be tracked how they combine and.
And by CPU, you mean like wall time usage, something like that, or clock time, I guess.
Yeah, I'm sorry, I don't have the information on that currently.
Hey, yeah, thank you for the talk. I wanted to ask about the safety multiplier that you introduced. Was it just like an empirical observation, like when the coefficient is like 1.2? Because like, I don't know, maybe you experimented with it, but I was thinking that you have the first requirement. Could you please, on the slide, there was like this first requirement about the, versatile 95, which is basically targeted to minimize under allocation. Isn't it the same thing for like why you introduce safety multiplier as well? Or maybe I'm misunderstanding something.
Yes, it was introduced with the same need to prevent the out of memory events and just to be safe.
Okay, so this coefficient is basically empirical.
Thank you. So the safety factor was introduced in the example sum. So we multiply safety factor for the example sum. So we used the setup for the hyperparameter optimization, and it comes to like we get a safety factor of 1.15 for the final model, but we also applied one more like 1.2 for reducing the number of the other location. As I mentioned, like it was 2.89, but in production we make it down to 0.3% for reducing the actual number of overlocation, and also for as a kind of final buffer for our page caching. So we don't want to slow down the build turnaround time. Yep. So that's why we use the 1.2. Okay.
All right, then. And I would like to thank Iva again for her talk.